Okay, so we're going to go over polynomial functions. What we're going to do is we're just going to go over the examples they have in your book. It looks like they got about 5 different ones that they have written down here. Okay, so one of the first functions that you should be familiar with is just a linear function. Okay, and essentially what's important about this one is it's to the power of 1. So you know it makes some straight line. Okay, so this one would normally go just like this, but the idea of it is we can add variables to this function, okay, and it can become anything. So we're used to seeing this function written as y equals mx plus b, and we know m being slope and b being the y-intercept. But in your book, the way they've written these things is a polynomial function in one variable is an expression in the form. So they've written polynomial functions kind of like this. They have a to the n, so depending on how many numbers there are, x to the n. And then what they're saying is from there, we can go down a value, x to n minus 1. Okay, so this expression or the way they've described them can be kind of confusing. So we're going to actually put numbers to them. And what they're trying to say is a is some coefficient, and x is some variable to a certain power, and this power can go up to like thousands, millions if we want. So the first one we're going to just talk about representing is this. And if you notice at the very end of this expression, the last thing they've kind of written, they'll put dot dot dot, and then they'll put a naught. In other words, saying that some constant term would be the last thing. That's what a naught stands for. All of the a's in this are actual numeric values, so they're numbers. And the x's stand for, well, our variable to some exponent. And what they're saying is when you list these, say this was to the power of 5, the next one you would list would be 5 minus 1. So this x, the next in order, would be 5 to the power of 4. They're just telling you how to put them in order. So what we're going to do is actually go about putting these in order using a linear function. So our linear function, like we said, can kind of be written like this. They have a x, and it's to the power of 1, and then you would just say plus, and they usually put a naught meaning some constant term. Okay, so this would be our linear function. Okay, and technically this would be a1 in this case. The next type of function you would have learned about probably in grade 10 is a quadratic function. And if you remember, that one starts with a squared, then what we have is an x to the power of 1, and then finally some constant term. So the same idea here is all they've done is they said you have a, we could say it's the second coefficient plus a to the first coefficient plus a naught again, being some constant term. And we can continue to go up and up and up with this. So this is a function we're a little more used to. We usually saw it like this, f at x is equal to x squared, and we know it represents some parabola, something like this. Okay, that would be our second one there. The first one was a linear, next one we had is a parabola or a quadratic function. So this is quadratic. Okay, we'll kind of highlight them for us. Linear was in yellow here. Quadratic functions are the ones we have in green. Okay, so these are quadratic functions, and again, a just stands for some number, and we could put examples in for this. An example of a linear function could just be f at x is equal to 3x plus 1. That would be a linear function. For a quadratic function, we could have f at x equals, let's say, 2x squared plus 3x plus 1. You know what we'll do? We'll just keep adding on to the original one we had. Okay, so we've just added another variable to it, and what it does is changes the shape of this function. The next one is a cubic function. Same idea, the only thing is we start with x to the power of 3, then we have x to the power of 2, then we have x to the power of 1, and then a constant term. And they would represent that with a3 plus a2 plus a1 plus a naught. Okay, you notice how we continuously just keep adding another term to it. Okay, and this is going to give us a completely different shape on a graph. We'll go ahead and check that out in a minute, what it's going to actually look like. But the general idea to this type of shape is something that actually goes up, comes down, and goes up again. Okay, So I'm going to do the new ones in different colors here. So quadratic and linear we're used to seeing, okay? And one way to look at it is the power of the polynomial, essentially the number of turns in the graph would be kind of one less than that, okay? So what I mean by that is if you notice, well, 1 less than to the power of 1, which is a linear is to the power of 1. If I go 1 less than that, that means there's no turns in the graph, okay? 0. 1 less than 1 is 0, so it's just a straight line. In a quadratic function, it's to the power of 2. So 1 less than 2 is equal to 1. So that means there's 1 turn in that function. So let's say we're going from left to right. It goes down, and then it turns once. That gives us an idea of a quadratic function. Okay? A cubic function is to the power, the highest power is 3. So 1 less than 3 gives us 2. So it's saying it has 2 turns. So again, if we're going from left to right, we go up, we turn directions once, and then we turn it again. Okay? So that's the idea of a cubic function. And essentially, every time we add a term to it, we just essentially add another term to the function. So let's talk about, so again, that was cubic. Cubic is our green function here. F at x is equal to, now we have x to the power of 4 plus 3. Wait, let me make sure I'm doing this. I'll just write them in and add the variables after. 3, 2, 1, and then some constant terms. So we know we're going to have 4 coefficients, A3, or A4, A3, A2, A1, and then probably some constant term. That's what, these are all standard forms, and this is called a quadratic function. Quartic, sorry. And what we're going to do with that is, again, because it's to the power of 4, 1 less than 4 is 3, so this one has 3 turns. Okay, so think of it like a function that goes down, 1 turn, 2 turns, 3 turns. So it almost gives us a W shape. Okay, and again, for every one we add to it, we'll do it. So the last one, I don't even remember what the 5th one's called. Quintic function. Okay. They have names for all of these, but the idea is you just want to get a feel for what these are going to be like. Okay, so all we're doing is adding another variable to each of the equations here. Oops, that should be the power of 1. And you know, there's going to be 5. They could be the same constants, but in this case, there's 5 different constants or coefficients. Sorry, not constants. And then there's 1 constant at the end, which is our a naught. Could be some term. Usually that's our y-intercept, right? So if this is a quintic function, have I done red yet? No, I don't think so. Function, okay. So this one's going to have 5 turns to it, or sorry, 4 turns, because we take 5 and we subtract by 1. So I'll try to do this one below, so it's a little easier to view versus the other one. So say we're going from left to right, we go up, we change directions once, twice, 3 times, 4 times, and that's that function there. Okay, so the amount of changes in direction of the function is related to essentially what the highest power of a variable is. That's what happens to all of these. So what we're going to do is we're going to bring these up and just kind of play around with them a little. We'll look at the originals of each. And what I mean by the original of each, I've written them all here. First one's just a linear function. This is x to the power of 1. If you notice, it's a straight line going through the origin. All of these will go through the origin, okay, because I haven't added anything else to them. We're used to seeing a quadratic function. It has 1 turn, okay? Now, I'm going to take away the quadratic and the linear just for a second, and we're going to look at a cubic function. Now, this kind of looks like it's only turned once, but it technically is turned twice. It's very hard to tell. So what we're going to do is we're just going to add a little to this function here. Let's see if we can't. Plus x squared. There you go. So I just kind of added a little to this function, and if you notice, it turns once and then twice. Okay, that's what's important about this here. The original one did technically do that, but it was much harder to see. Okay, so as we play with these functions, we're going to see that they change different direction. The 4th one here, I'll turn it on, almost looks like a parabola. It looks like it's, again, only turning once, but it's actually turning 3 times. And what we're going to do is we're going to add a little to this function, like we said. Let's say 5x cubed plus 2x squared. Let's see if that gives us anything. Oh, this one. That's so hard to tell. Let's change this number here. Zoom in a bit. No, still hard to tell. We'll play around with these numbers here until we get something that is somewhat 2. Let's just add an x. Okay. If we change the coefficients to each, we should be getting a 4 function. What we'll do is, okay, take that coefficient away. Let's just see if we can add x cubed to it. So starting to turn a little. X squared. No, it just goes right back to it. If we can zoom in, we can kind of see this. It should show a nicer function that has a more pronounced turning. But if you notice, this function from left to right is going down, turning once, then it technically turns twice, and then a third time. It comes back up here. What would be a good function? Let's see if they have one for us. Not really. We'll get into it after, I guess. Okay. So that's our quadratic function. This would be this one here. If you notice, it changes 3 times. 1, 2, and then 3 times it changes direction. So that's the idea of it. And then the same thing said for here. Now this one almost looks like a cubic function again. It looks like it's only changing once, but it's actually changing direction when we get into it 4 different times here. Let's play with some numbers. Let's hope that x to the power of 4. Oops, no. X to the power of 4. Doesn't do much. Minus 5 x to the power of 3. Let's see if that does anything for us. There we go. We just need a couple negatives. Oh, this one really took off. Change that value to 1. There you go. 1, 2. No, only looks like 2 still. There you go. A little bit better. So if you notice when we go left to right, this goes up, change the direction once, comes down, change direction twice, 3 times, 4 times. Though they're not very pronounced, we'll try to zoom in a little. These are changes in direction. Okay. So essentially the idea is for every variable exponent we add, the graph in general just changes a direction another time. Okay. So that's what we got to get used to looking at.